Hi, in this video I try to explain Thevenin's theory. It's actually much more simpler than it seems in textbooks. So this is all that it says. Assuming I have a very complex circuit, let's say the wiring of my house with some AC source or DC, let's stick to DC for now, or any voltage source at all, works for both AC and DC, with a lot of bulbs and loads, very complex sockets, wiring. Okay, so you get a point. A very complex circuit. Now, without analyzing the whole circuit, assuming we wanted to find the current in this node only, all that Thevenin is saying is that we can represent this whole circuit with an equivalent circuit that looks like this. A single voltage source, we call that Thevenin voltage. Obviously, it was a man who discovered it, so we put his name there. And a single resistance called Thevenin's resistance. And our point of interest comes right here. Okay, so this is what Thevenin says. We can take out our bulb and put a voltmeter here. Then we measure the voltage and write it down. After that, we put, so that voltage becomes our Thevenin voltage. After that, we put an ammeter here. You measure the current and put it down. So that becomes the current through this guy here. So then we can solve for the resistance here. And that becomes, using Ohm's law, 2 V is equal to IR. And that is 2 ohms. So then, if we now place our bulb, assuming our bulb is a 1 ohm resistor, we place it here, then we can easily find the current through our 1 ohm resistor, not this one. So it's now going to be V is equal to the total resistance. So V is equal to I is equal to V over R, which is going to be 2 over 3. So now let's try some real example and see if indeed this method works. Alright, so as we have this circuit here, I want to use easy values, 10 volts, and there is 100 ohm resistor, another 100 ohm resistor, and another 100 ohm resistor. So we want to solve and know the current that is going to pass through this 100 ohm resistor. So like I said, we treat this as a bulb and we take it out. So first, let's draw Thevenin's equivalent. So this is our node of interest. We call it AB. Okay, so we are going to put a voltmeter here. after we take it out. For a voltmeter, you can decide not to take it out, but let's just take it out. And I put my voltmeter here. Okay, so now what voltage am I going to read? Okay, if you are not familiar with voltage divider, you can quickly do that here. Assuming I have in series 100 ohms, another 100 ohms in series. Let me stand that value 50 ohms. Now because they are in series, they are going to share the voltage proportionally. So the voltage across this 100 ohms is going to be 100 over the total, which is 150, times the total voltage, which is 10 volts. And this is going to see 2/3 of 10, 6.667 volts. Then you can subtract to get what will be here, or you can just do 50 over 150 times 10, which is 1/3 of 10. Okay, so you get a point. So this is called a voltage divider. You use that to share voltages in series. So now our equivalent circuit here, let me just redraw that. Our 10 volts, then the 100 ohms, and the 100 ohms, now because we've taken this out, because that's what we are interested in, we are just putting, change the color of the pen, we are just putting a voltmeter here to measure the voltage across this node AB, which will be the same voltage across this guy. So from voltage divider, they are going to share it equal. It's going to be 5 volts here, 5 volts here. So the voltage across the node of interest is 5 volts, and that becomes our Thevenin voltage. Then we now put an ammeter here. Okay, so let me tell you something about ammeters as well. Let me redraw that to make it clean. So the same node AB, I put in an ammeter, 100 ohms, 100 ohms. So mind you, these are the 200 ohms in question. This has been taken out. We want to eventually find the current through the third 100 ohm. Okay, so we want to use our ammeter to find the current that will flow through that node we left behind after we took out our resistor. And a little information on ammeter. So an ammeter has ideally resistance equal to 0, and a voltmeter has ideally resistance equal to infinity. So what that means is, in this connection, the ammeter will act like a short circuit. So a short circuit is just a wire. We draw the circuit. Okay, so we have 100 ohms, 100 ohms, and our ammeter is here. But remember, I said the ammeter is like a resistance of 0. So whatever current is flowing through this branch is what my ammeter is going to read. That's something you get used to. If you don't get it now, trust me, if you are pursuing an engineering program, you would understand this. So a simple ammeter has a resistance of 0, a voltmeter has a resistance of infinity, making it an open circuit, and an ammeter a short circuit. So let me write that here. So voltmeter short circuit, sorry, open circuit, ammeter a short circuit. Okay, so we have an ammeter connected here. How do we know the current going to flow through the ammeter? To IA. Alright, so when the current is coming through from here, passes through this branch here, but when the current gets to this node, now we know current, like most engineers, is very lazy. So there's a lot of resistance here, but there's no resistance here. So all the current are going to flow through this branch and ignore the resistance branch and goes back to the source. Okay, so if you are familiar with the current divider rule too, you could do that. To the current divider rule, instead of sharing proportionally, so let me quickly do that. So current divider rule, current divider rule. So assuming you have current coming in, and it's supposed to share between two branches, R1, R2. If you wanted a current IR2, that's going to be the current that they are all sharing times. Now instead of sharing proportionally, you take the other one, which is R1, over the sum, R1 plus R2. So this is IR2. Take note that you take the other one here, unlike voltage divider where R2 would have been here. Alright, so in this case, since R2 is 0, a short circuit, then the current through I2 is going to be all of R1 over the sum, which is everything. Okay, so we can calculate the current through, and that becomes Ohm's law. So it's going to be, since everything is going through, so we say this guy has been short circuited out, so the current I ammeter is going to be 10 volts over 100, which is 0.1, which is 0.1 amperes. Okay, so what we do is, now we have our Thevenin's voltage 5 volts and our current is 0.1 amperes. We use these two to find our VTH, RTH, and that's going to be V is equal to IR over I over I. Then we have .500 ohms. Sorry, 50 ohms. And that's it. We found the Thevenin equivalent circuit. So now if you want to find the current through this branch, you just replace your 100 ohms, put it back, then you find the current Ohm's law. So this time they are in series, so it's going to V is equal to IR. Our R is 150 in series, and our V remains 5, the Thevenin voltage. So it's going to be 5 divided by 150 going to be our I, and that is 1/30 amperes. So let's prove if that is true. So initially I had 10 ohms with 100, another 100, and we wanted to find the current in this last 100. Okay, so we can use different approaches to solve the current, and we should have the same answer. So one approach I want to use is I want to combine these two because they are in parallel, and if they are in parallel, they will have the same value. So it's going to be, no, sorry, we have half, so that's 100 parallel 100, product over sum 100 times 100 over sum, which is 200. So that's going to be 10,000 over 200, and that gives me 50. So circuit looks like this. And the current through this 50 is going to be current that's going to be shared between the two of them. Okay, so what do we have? We have our 150 over 10, um, 10, 150, and that's 1/15 amperes. So now I come back here, so it means I have over here 1/15 amperes. This is just to prove the concept. So, and originally we had 100 and we had another 100 here. So what current will flowing through this current divider to IR2 becomes the total current 1/15 amperes times the other, this one, over the sum of the two, which is 200, and that gives us 1/30 amperes. Okay, so you see how easy Thevenin's theory is. So let's wrap it up. So Thevenin says no matter how complex the circuit is, you have a complex circuit and you just want the current through a particular node, all you do is step 1, take out the node and put a voltmeter there, measure the voltage and call that the Thevenin voltage. Step 2, take out the node as is already taken out, replace it with an ammeter, measure the current flowing through that and call that, I don't know, you can't call that Thevenin current, just write it down. So measured currents, so IA measured. Then the Thevenin resistance can be calculated easily by doing RTH is equal to VTH over I measured. Then you solve, you can put your bulb or your resistor here and you solve for the current easily using Ohm's law. Okay, so that's it. Hope you enjoyed it. Don't forget to like and to subscribe. Bye.